Okay, in order to understand the atmosphere, you've got to find out where all the energy comes from. All of the Earth's energy comes from the sun. So we would have no weather without the sun. So you got to understand that the energy from the sun comes in the form of solar radiation. And that radiation is in form of electromagnetic waves. Think about it. If you have a microwave oven, you have something similar happening with microwaves hitting the food, warming it, making it hot, ready to eat. Well, that's what radiation is. It's a form of energy transfer. And the sun is great at that. It is extremely hot and transfers a ton of energy. But there are some other ways that energy can be transferred. There's conduction. Have you ever touched a really block of ice? Your fingers get real cold real fast and you move them away. That's conduction. It's just a transfer of energy when two surfaces touch each other. Take your plane. If you touch it and the wings, you're transferring energy between your fingers and the wings. There's a conduction going on. There's another form of energy called convection, and another one called advection. Advection is very simply when things are moved along to transfer energy. Say you wanted to warm a surface, and let's say you had a frozen water pipe. What do? You turn on a blow dryer to heat that water pipe. That's advection of warm air because the air dryer is putting out hot air and you're blowing that air on the pipe, trying to warm it up. That's in simplest terms advection. Warm advection means warm air is being transferred to you. Cold advection means being cold air. In the wintertime, cold front passes your house, it gets extremely cold. That's cold advection. Convection, if you ever look outside in the summertime especially and see the big building cumulus clouds, that's convection. That's warm air from the surface being lifted upwards, expanding as it's going. That's convection. It's just a circle of air moving up and down. If you see bubbling water, it's another form of it. So let's go into a radiation a little bit and understand solar radiation is not trivial. But we like you to just have a little bit of fundamentals. So with this, I'm going to move on to another slide I like better for this. So when you're looking at the sun, think about it. If you're at the equator, it's perpendicular to you on the equinox days in March and in September. If it's perpendicular, if you put a flashlight, point it directly down at the ground, what do you get? A very small circle. But if you move it at an angle, you get a much broader circle. Oh yeah, but only the same amount of light has come out of there. So the same amount of energy is coming out. It's just getting spread over a larger area. So think about it. The sun's at the equator. If you're getting at the equator, you're getting a powerful dose of sunshine. However, if the sun's directly at the equator and you're up, say up here in Beckley, where's your sun coming from? It's at an angle. So you're getting your radiation is spread out. You're not getting as much radiation at one point as you were at the equator. That's the first concept I want you to get. The second one is we're going to rotate this wonderful Earth of ours around. All right. The Earth is in an elliptical orbit about the sun. So with that, here is an image of how the Earth is tilted. When it's equinox, kind of the tilt is at an angle to the sun. It's not directly towards the sun or directly away from the sun. It's at an angle. So the sun is direct right on the equator. Now, winter solstice, the southern hemisphere pole is towards the sun. The northern hemisphere pole is away from the sun. So what happens? More radiation coming in the southern hemisphere, a lot less radiation coming in the northern hemisphere. So you can see throughout the year the transition of how the radiation is distributed. Energy is not coming in nice and simple at the equator, and it's not coming not at all at the poles. It's transitioning throughout the year. That's what causes a whole bunch of fun weather to happen. So let's go back to where we were, moving forward here a little bit. So we've learned all about radiation coming in. We're going to talk a little bit about waves. Remember, think of a wave like a wave in the ocean. And that's what really is an energy wave. So if you think about it, the wave goes down when it's going by you, and it goes real low, maybe down to your knees. All of a sudden, this big thing looks up to you can look back at it and say, oh, that's way above my head. That's the crest of the wave. So you have a trough and a crest. And the distance between two crests or two troughs is the length of the wave. All electromagnetic radiation moves at the speed of light. So therefore, you can immediately go C equals F times L and learn both. If you know frequency or you know wavelength, you can learn the other. So, and one of the interesting things is, you think about it, we see each other in color. Almost all the sun's radiation comes in the color spectrum. So that's a key point as well. So that's radiation coming in. But guess what? That radiation just doesn't just come in simply. Some of it bounces off the atmosphere. Oh yeah. Some of it might bounce off a cloud further down. Some of it might get absorbed by gases like greenhouse gases, like carbon dioxide. All of this radiation, however, eventually some of it gets to the ground. So you can see there's a complex amount of how much radiation is getting down to the earth. And then guess what? The earth, to maintain the temperature we're at, must re-emit that same amount of radiation that we receive every day if at a given temperature. If the temperature is going to go up on average, and it's not that much, we would be changing the amount of energy emitted back into space. And we can look at that over time, and it's pretty standard. So what happens is, say you have radiation coming from the Earth, it might hit a cloud above you and bounce back down some of that radiation. Some of it might scatter all over the place. Some of it might get absorbed by the carbon dioxide, the greenhouse gases. When that happens, some of that radiation comes back down to Earth to heat us up more, and some of it goes back into space. So the greenhouse gases act as a way of keeping us warmer, which in many ways is a good thing. Conduction and convection move the temperatures around, energy transfer. Think about it, if you were on a bridge and you've all seen the signs that say bridge freezes before road surfaces. Well, what's happening is conduction is occurring. Think about it. If your temperature is really cold, on both sides of that bridge, there's conduction occurring. So that temperature of that bridge is dropping real fast. However, over the land, the roadway, you have warmer land surface hitting the surface of the colder air above it through the roadway. And what you're winding up doing is you're getting heated from below the road and you're losing heat above the road. So your road doesn't cool as fast. You have conduction occurring. There are all kinds of temperature scales out there. Celsius is one I kind of like to use, but we'll use Fahrenheit throughout the course because the U.S. stays in Fahrenheit. And there are all kinds of temperature measurements, ways of looking at weather that way. And we've just talked about the global distribution. Now think about it. In the wintertime, there's colder temperatures up towards the North Pole in January. significantly colder over Siberia, over the North Pole. You can see the temperature gradient. Temperatures over the tropics don't change a whole lot. So you can see there's a real tight temperature gradient there, right over the tropics. And then when you get to summertime, there's less temperature gradient. Kind of warms up to the north and cools off, a little more temperature gradient down to the south. These temperature gradients are going to play a big role. Upper air, same principle applies, how it changes through the year. So with all of this being said, here is, for example, how really good example of how radiation impacts temperature. Here is Barrow, Alaska. Look at it. It hardly sees any radiation during January and February. Temperatures are pretty uniform. This is the normal temperature range here. However, the little bit of highs and lows this year, observed temperature range was a little bit more, but the average is not much. All of a sudden, sun comes out, boy, it starts going up. So you can really see the temperature, what we're learning about here, being applied in everything we're doing. So hopefully you got something out of all this. Just looking quickly at the weather map, here are the temperatures. So for example, Parkersburg, West Virginia, 77 degrees, 73 degrees here. If you wanted to know about advection, look for the wind, which is the barbs, and see which way it's blowing. And is the air from the direction it's blowing warmer or colder? That's going to be advection. So I hope you got something out of all this. And again, as every week, I want you to let me know if you have any questions.